Flipped classroom video for Maths AS Unit 1, Circles, Applications. So we're often interested in the relationship in certain geometrical situations between circles and lines, and tangents of course very much play a part and are very important in that. So finding the equation of the tangent to the circle at a particular point is a useful technique to know. So we're going to have a look at a particular one. We're going to find the equation of the tangent to the circle x squared plus y squared plus 4x minus 8y minus 5 equals 0 at the point minus 5, 8. Okay, so the first step is we can find the gradient of the radius to the point. And to do that we need to know the centre of the circle. So I'm going to do that by quick completing the square. So I've got x plus 2 squared minus 2 squared and y minus 4 all squared minus 4 squared. Take away the 5 equals 0. Therefore the centre is at minus 2, 4. I don't need to go any further to get the coordinates of the centre. And then through using ordinary coordinate geometry, the gradient from the centre to the point is the difference in the y coordinates, so that's the 8 from the minus 5, 8, take away the 4 from the centre, and then on the bottom I've got the minus 5 from our point on the circumference, take away the minus 2. That gives us 4 over minus 3, which is minus 4 over 3. Okay, step 2, find the gradient of the tangent. Well, we know that the tangent is at right angles to the radius from the point where the tangent meets the circle, so that means the gradient of the tangent times the gradient that we've just worked out, the gradient of the radius to the point, which I called mr, they must multiply to minus 1, which means that mt is minus 1 over minus 4 over 3, or 3/4. Flip it up and negativize it is another way of looking at it. Okay, so we now can start doing a little bit of a sketch. It's always worth doing sketches in coordinate geometry and circle geometry and geometry in general. The clue is in the name. So we're going to mark the centre on, so that's minus 2, 4, and we're going to mark the point minus 5, 8, and we're just going to do a bit of an arc there because what we're interested in is the equation of the tangent to that circle, and we can get a rough idea of if our answer is looking reasonable from this sketch. So let's have a look further. Well, there's the tangent. So we're looking at a gradient around 1. It looks around 1, and the one we've calculated is 3/4, so happy with that. We're also looking at an intercept there for 8, roughly 12. So let's have a look at that. Step 3 is find the equation of the tangent. So we use our trusty old friend, y minus y1 is mx minus x1. We have all the values we need. x1, y1 is the point minus 5, 8, so they get popped in. M is the gradient, of course, 3/4 that we just worked out. Times 3 by 4 gives us 4y minus 32 is 3x plus 15. Of course, that minus minus becomes a plus. And that means we have 3x minus 4y plus 47 is 0. Now that doesn't particularly help us with that intercept, but we can, if we want, from that point or from where we've got to, doesn't really matter, it's easy enough either way. If we want to get it into y equals mx plus c form, so we have the plus c, we can just do y equals 3/4 of x plus 15 over 4, which is the 3/4 times the minus minus 5, plus the 8 from the other side, and when we tidy that up we get 3/4 x plus 47 over 4, and of course 47 over 4 is about 12, so that means we're happy with our answer because it matches to our sketch and sort of vice versa. Okay, moving on, we often will have a line intersecting a circle and we may want to find where they intersect. So our example is going to be find the coordinates of the points where the line y equals x plus 5 intersects the circle x squared plus y squared plus 6x minus 4y minus 5 equals 0. Step 1, we substitute the equation of the line into that of the circle. So the usual sort of technique for solving simultaneous equations. They both have to be correct at the points of intersection, both have to work for the points of intersection. So if we equate them in this way, then that will give us those values. So what that means is the y for the y squared has to be replaced by x plus 5, so that gives us x squared plus x plus 5 squared. Then we've got our plus 6x, and then the minus 4y becomes minus 4 brackets x plus 5. Then we've got take away 5 equals 0. Step 2, tidy that lot up and solve it. We can see that we've got a quadratic in x. The highest term we're going to have, the highest power, is going to be x squared. We're going to have x's, we're going to have constants, so we are going to end up with a quadratic. So we just need to take the time to work through that. So we've got our x squared. X plus 5 squared is going to be x squared plus 10x plus 25. Then we've got our 6x. Minus 4 times x plus 5 is minus 4x minus 20. And then our minus 5, and that's equal to 0. Now we need to gather up our bits. So there's our 2x squared. We've got 10x plus 6x minus 4x. That gives us plus 12x. Then, rather handily here, and this won't always happen, but we've got 25 take away 20 take away 5, so 0. I've written it in just for completeness, and that equals 0. And that means we can say that we can divide by 2, therefore we've got x squared plus 6x is 0. We can factorise that straight away. X times x plus 6 is 0, and that tells us that we have either x is 0 or x is minus 6. Step 3, find the other coordinate. And of course the easy way of doing this is to put it into the equation for the line. I have, as you might imagine, seen it put into the other equation, which means that you just end up having to solve a quadratic in y, which is a bit of a waste of time when you've got a very easy y equals x plus 5. So y equals x plus 5. If x is 0, that gives us 0, 5. And if x is minus 6, that gives us minus 6 minus 1, because minus 6 plus 5 is indeed minus 1. And we'll have a little look at a picture of that. And that is in fact a diameter as it happens on this question. But you can see that that's worked out okay. And that, I've lazily, in a way, just whipped it up on GeoGebra. But you should be doing little sketches like this by hand as practice. Also playing with GeoGebra, because that's a very useful tool for building up your intuition. And I've just said all that, so there's your lozenge to have a look at as well. It's a good idea to sketch solutions. For this question, you'd have to find the centre and radius of the circle first. So that will be an extra bit of practice as well. Okay, moving on. Prove a tangent. So prove that a particular line, in this case 4x minus 3y equals 33, is a tangent to a particular circle. In this case x squared plus y squared minus 10x minus 8y plus 16 equals 0. So how can we do that? The second thing they want the actual coordinate to the point where the tangent and the circle meet. And actually that second bit gives us a bit of a clue, because what we know about the tangent is that it's a line which only touches the circle at one point. But it definitely does touch, so if we solve them simultaneously as we did before in the last question, then things should become clear. So first of all, we substitute the equation of the line into that of the circle. We'll do a bit of fiddling first, because we haven't got such a simple line as we did before. So 3y equals 4x minus 33, and that means y is 4 over 3x minus 11. So from the equation of the circle, each of the y's are replaced by 4/3 x minus 11, as you can see there. You can work through all the actual nitty-gritty of this yourself with your own pen, but we next need to tidy up and solve this, which is a bit of a job, but that's maths for you. 4 over 3x squared is 16 over 9x squared. We've got 2 times 4 over 3 times minus 11 gives us minus 88 over 3x, and then we've got minus 11 squared is plus 121. There's our minus 10x. Then we have 8 times 4, so 32 over 3x, which is minus 11 times 8, which is plus 88, plus the 16 is 0. Then, to make life easier, I've times through by 9, and you get all that lot, and you'll have to trust me on that. You can check it yourself. But that then tidies up to 25x squared minus 450x plus 2025. And these numbers are looking a bit horrendous, but if we divide by 25, and we can see that they all divide by 25, because we've got 25 for the x squared, we've got 50 at the end of the coefficient of x, and we've got 25 at the end of the constant, so divide by 25, that gives us rather nicer x squared minus 18x plus 81, and you may notice that 81 is 9 squared and 18 is 2 times 9, so that in fact tells us we have x minus 9 all squared equals 0. And therefore we've shown that there is only one solution. That means there's only one point of intersection of the line and the circle, and that means that the line is indeed a tangent to the circle. So we have proven the first part. We now need to find the coordinate of the point where the tangent and circle meet. Well, we know what the x-coordinate is because it must be 9. We can just write it down, so x minus 9 squared is 0, tells us that x equals 9. Then we need the y-coordinate, so we put that x equals 9 into the equation of the line, of course, because it's much easier. And we get minus 3y is 33 take away 36. That means minus 3y is minus 3, and that means y is 1. And that means the intersection, so that sort of upside down u or a funny sort of n, is the symbol for intersection, which is about to come up in a lozenge. There we are. That's the symbol for intersection, which you may or may not have come across. But what that's telling us is that therefore the intersection point is the point 9,1. Now this is a really interesting aspect of circle geometry, and that is when we have two circles and look at whether they intersect, and if so, in what way. So the question is, how can we tell if circles will intersect? And we could draw them, of course, but is there a way of telling without drawing them? I would stress that sketching them is probably a good idea in any sort of question or problem-solving situation, but let's have a look at it in a sort of abstract way. So if we imagine circles approaching each other, then the first situation we might have is that they're approaching, but they haven't touched or crossed each other yet. And in this situation, there's no intersection, of course, and the distance between their centres is greater than the sum of their radii. So if we know that the distance between the centres is more than the sum of the radii, we know that they can't intersect, so whether we sketch it or not. The next thing that happens as the circles approach, and I know they're changing, so there are different circles in each of these diagrams, but the next thing that will happen is that they will just touch. And in this situation, we have one point of intersection, and remember that slightly odd N shape is the symbol for intersection, and one point of intersection therefore touching externally, so the circles are external to each other, and in this situation the distance between the centres is exactly the same as the sum of the radii. The next thing that happens is that the circles will intersect in two places, but the distance between the centres is now less than the sum of the radii. But there's something else that's starting to happen as well. In this situation, if we look at the difference between the radii, that is less than the distance between the centres. But that's going to become important on the next picture. It's also worth pointing out that that condition of the centres being greater than the difference between the radii is also a condition that holds in the previous two situations. Sort of obviously in a way, but it's worth pointing it out. So let's have a look at the next situation. Now the circles have moved. I'm imagining the left-hand one moving for some reason, but it's moved across towards the right, and now it's just touching the larger circle in one place. So what's the conditions here? We have one point of intersection, they're touching internally, and what we have here is that the distance from the centres, between the centres rather, is equal to the difference between the radii. I've actually, I think, got that RB minus RA the wrong way around. It perhaps should say modulus of RB minus RA, but take it as just the difference between them. And what we can see is that if we do the distance of the radius of A, so going from the centre of A to the point of intersection, if we then subtract the other radius, that will take us back to the centre of the other circle. Hence, the distance between the centres is in fact the difference between the radii. It's also still the case, of course, that the difference between the centres is less than the sum of the radii now, and so that condition carries on, even though this new condition of thinking about the difference between the radii has become more important in a sense. So of course the final situation is that the circle moving to the right has entirely been engulfed by the other circle, so there's no intersection. This time we have that the distance between the centres is less than the difference between the radii, and it's still also the case, of course, that the distance between the centres is less than the sum of the radii as well. So by looking at all of those situations, that's all the possible situations there are with the greater than equal to or less than the sum of the radii, or greater than or equal to or less to the difference between the radii. And so that's an overall complete summary. Let's have a look at an example. The following pair of circles touch each other. Find possible values of B. Okay, well you'll notice there the two circles are expressed in different ways, but never mind, we can deal with that. So, for the circles to touch, we need the distance between them to equal RA plus RB, to equal the sum of the radii. Or, that's for external touching. For the internal touching, we need it to equal the difference between the radii. The first step is find the centre and the radius for each circle. Now, I perhaps should have marked them as A and B earlier, but never mind. I'm going to call the top one A and the bottom one B. So for the top one, we can see straight away the centre of that circle is 2, B. That's in the standard or general form rather of the circle equation. I can also read off that the radius is the square root of 9 and is therefore 3. For the circle B, we have to complete the square, which gives us x plus 2 squared minus 2 squared plus the y squared equals 0. And then we can put that 2 squared, add it to both sides, and we get x plus 2 squared plus y squared equals 4. That means the centre is minus 2, 0, and the radius is the square root of 4, which is 2. So we've got all the information we need. We can now calculate the distance between the centres, and so we use ordinary coordinate geometry, difference between the x's squared plus the difference between the y squared, all square rooted. That gives us 2 minus 2 squared plus b take away 0 squared, which is 16. So that's the 2 minus 2 is 4, squared is 16, plus the b squared. So that's our distance between the two centres. Now we also need to calculate the two different sums, the RA plus RB, and then the difference between the radii, which we're going to use to work out whether any of these touching things are possible. The sum of the radii is 5. We can see that straight away. We've got a radius of 3 and a radius of 2, so the sum is 5. The difference is the 3 take away the 2, so in fact it was RA take away RB. Doesn't really matter. So we've got a 5 and a 1. Now, now we're looking for solutions for our value of b, because we know that the square root of 16 plus b squared, which is the distance between the centres, has to either equal 5 or 1. But in fact, that square root has to be bigger than 4, doesn't it? We're only interested in the positive square root. B squared has to be positive, so the number inside the square root has to be bigger than 16, which means the square root itself has to be bigger than 4. So it isn't possible for the distance between the centres to equal the difference between the radii. So it can't equal 1. That means we are only dealing with this case of the distance between the centres equaling the sum of the radii. So that means we've got root 16 plus b squared is equal to 5. That means 16 plus b squared is equal to 25. That means b squared is 9, and that means b is plus or minus 3. And of course, that can be plus or minus 3 because that's part of a coordinate. So it's the y-coordinate for the centre of the circle A. And you should have a go at sketching this, and or looking at it on GeoGebra. On GeoGebra, you could use a slider for b, so you could be moving circle A, and to see what values of b then mean it just touches circle B, and certainly it'd be worth having a go at sketching it.